Let's start with a simple question. Why even care about RC oscillators? In many chips, especially low power SoCs and sensor nodes, we need some kind of clock. Crystals work well, accurate, low jitter, but they are bulky and external. MEMS? Well, the MEMS itself could be smaller, but still not fully integrated, and could still be bulky after integration. What if we just use the CMOS process and build an oscillator with only R and Cs? That's our journey today. Compact, cheap CMOS native clocks. Before diving into circuits, think of this as a trade-off triangle. Integration, stability, and simplicity. RC oscillators win on integration and simplicity, but they lose to crystal on precision. Still, in systems where plus minus 0.5% is good enough, an RC oscillator can be a perfect fit if we engineer it well. The most basic type is a relaxation oscillator. You charge a capacitor slowly, hit a threshold, then discharge it. Repeat forever. It's easy to understand. It's like filling and draining a water tank between two levels. But the design pitfall is in the detail. Comparator delay and offset mess with your timing. It's not a concept, but the implementation imperfection that hurt. Let's pause here. Suppose your comparator reacts a bit late, after the capacitor already overshoots the threshold. That delay adds to your period. Worse, the delay itself changes with temperature and supply. This is what causes frequency drift. Not just a static error, but a dynamic one. So, delay equals instability. But why not just use a faster comparator? Good question. You make a faster comparator, but you pay for it with power. This becomes a design trade-off: accuracy versus energy. In many low-power designs, you cannot afford to spend microwatt on precision comparators. So instead of brute force, can we explore compensation techniques in the dynamic behavior? Bingo! Instead of fixing the comparator, we shift the target. If the delay causes overshoot, then lower the comparator threshold in advance. Use a feedback loop to track the average DC voltage and adjust the comparator input so that the charging-discharging waveform always ends at the right level. It's like aiming ahead of a moving target. Any other offset compensation? Right. Another elegant idea. Flip the comparator every half cycle. If the offset is plus 10 mV in one direction and minus 10 mV in the next, they cancel out when averaged. This technique, inspired by chopper stability amplifiers, works well for mitigating static offset errors. Then, can we move to an open loop topology? Right. Despite all this, open loop design still cannot go below 1000 to 5000 ppm reliably. Why? Because they are still limited by physical delay and offset, factors that are difficult to model accurately and calibrate in production. That's why we turn to feedback. We borrow the concept from a pure design. If you can measure frequency via frequency to voltage conversion, then compare it with a stable voltage reference, you can use the feedback loop to lock the oscillator. The frequency becomes a function of a known quantities: resistor, capacitor, divider ratio, not device mismatch. The loop removes the dependency on delay or threshold. Then, how to implement it? Yeah, here's the trick. Build a resistor out of capacitor and switches. A switch capacitor resistor has an effective resistance of 1 over Fc. So, as the oscillator's frequency changes, the resistor value changes. Combined with a resistor divider, you build a frequency to voltage converter, FVC. This creates an error voltage for the loop to minimize. Any issue with it? Bingo! We fixed the delay and offset problem. But now, something else causes frequency drift. The resistor. If the resistor's value changes with temperature, the frequency changes too. Capacitors usually stay stable, but resistors can vary a lot. So, if we want the frequency to stay steady, we need to keep the steady too. But how to? Right, a basic way: combine two resistors with opposite temperature coefficient in pair. Adjust their ratio so that drifts cancel out. This method works, but the tuning is cost. You will also face changes like resistor spread and switch parasitic. What else could we improve? Correct. Here's the elegant solution. Instead of using physical resistor arrays, use one resistor plus one switch, but turning the switch on off with the PWM or pulse density modulation signal via sigma delta modulation. The resistor's effective value becomes tunable with infinite resolution. This gives precise control with minimal area and noise. So use two temperatures, let's say minus 40C and 85C, and measure the oscillator frequency under two configurations. For this, solve for optimal weights A1, A2 for the two switch resistors. Store the values in digital trim words, down ones in test. This keeps the oscillator stable for life. Well, almost. Is that true for the lifetime? Correct. Let's not forget aging. Over years, resistor's value can drift due to stress, electromigration, or charging trapping. Even the best compensation don't help if the reference resistor itself changes. So the next frontier is aging resilience design. There are three tricks could help. Duty cycling a reference oscillator so that it resets most of the time. Alternating current direction through the resistor to reduce stress. Occasionally correction of the main oscillator by comparing to a fresh one. It's like giving your circuit a nap and a checkup. Smart, low cost, and effective. Here are a summarized images showing you why you may need RC oscillators. Intuitively, they are small, cheap, and fully integrated. So, with smart techniques, feedback loop, switch resistors, calibration, you could possibly achieve 100 to 200 ppm stability in CMOS. For many applications, that's not just good enough, it's ideal. Crystal may win on absolute accuracy, but RC wins on integration and cost. with enough care, they can serve well even in challenging environments. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting from it.